Hello, my name is Chan. I'm from Cisco Networking Academy, MMU. This is our website. You're free to visit our website. All right. Today we're going to talk about fiber optics. In the physical layer on the fiber optic, basically this is the light signal. The light signal is in this wavelength form. Right. If you look at the ray model of the light signal, you have an index, refraction index, where n is equal to the speed of light in the vacuum divided by speed of light of the material. So normally the light will travel in the straight line. It will travel in the straight line, okay? In all direction, but in the straight line. So this is the index refraction on the A, is 1. In the glasses is 1.5, diamond is 2.4, and water is 1.33. So from this index refraction, you know that light travels slower in glasses, all right? Slower in water. Reflection means bending of light. Bending of light. In Malay, you call it biasan. Biasan, all right? Refraction, all right? So there's another thing you call a reflection. Reflection in Malay, you call it pantolan, all right? So it's a bouncing of the light. So in reflection, when you put an angle theta 1, all right, it will reflect it back on the same theta 2. Theta 2 is equals to theta 1, all right? It's always at the same angle, all right? So this is the angle of reflection, all right? This angle has to be same for each pair of ray. So this ray will come here, it will reflect it over here. This one come at this angle, will reflect it at this angle. Then you talk about refraction. Refraction means that when you put a light source from the glass to the A, some of the light will be reflected, some of the light will be gone out, missing, refracted, all right? So you can see over here, some of the light will be reflected, all right? So you can see if the index, refraction index of A is more than the glasses, then theta 3 will be more than theta 1. So let me explain it on the board a bit, all right? All right. So normally it's like that. Oh, cannot see. Normally like this. Okay. Normally it's like this. So this is the glass. This is the air. All right. So when you put in the angle like this, it will go like this. Okay. So this one is bigger. This one is bigger than this one. Than this one. Okay. Than this one. So if after a certain point, the angle will be like this. Okay. Then after this theta, all the light will be 100% reflected. Okay? So this is what we want inside the fiber. This is what we want, 100% reflection. So if it's 100% reflection, the lights will stay inside the fiber. That's what we want. Okay. Let's resize this. Okay, so this one, if at certain angle, some of it will be reflected, it will be like this. So there's a loss of energy. So what we want is that we want full total internal reflection. So full total internal reflection means that we will send the light at a specific angle, more than the critical angle, then what happened? All the light will remain inside the core of the fiber. So when it remains inside the core of fiber, the energy is still with the fiber, inside the fiber, so you can transmit a longer distance. So that's the concept, total internal reflection. Okay, so you can see after first theta 1, you can see some of the energy go up inside the air. But after when you reach theta 3 is the critical angle, it will be totally internal reflected. So this is what we want inside the fiber. All the light is reflected inside the fiber itself. Okay. So if you cut the fiber out, then you can see the light will go out in all direction. Then you can see there's this theta. So this is the angle, the range of angle that is totally internally reflected. All right, the light that is totally internally reflected. This example of a multimode fiber. You can see a coating, clay, and you have a core. Okay. So this is about dB. So the formula for dB is this one: 10 log 10 power final over reference, or 20 log 10 voltage final over reference. All right. This one we're going to do later on. Okay. In multimode fiber, the core is very big. The core is very big. So the core for multimode fiber is what is it? 62.5 nano micron. Okay, if I'm not mistaken, it's 62.5 micron. All right. So this one is for multimode fiber. So the core is very big. So when the core is very big, a lot of light can go inside. A lot of light, because you have a big hole, bigger hole. If it's a single mode is around, 9 micron, so it's a lot more smaller. The diameter is 9 micron compared to multimode. So in multimode fiber, normally you have two fiber, one going at this direction, because the light travel straight line, isn't it? So basically you need a pair of fiber to transmit. Okay, if you have a connection between two ports, normally there's two fiber connecting, one transmit, one receive. All right. This is a fiber stick and twist. All right, you can see you stick it and you twist it. All right. And this multimode fiber. Okay, the multimode fiber, you have two types. One is a loose tube construction. All right. Another one is a tight buffer construction. Tight buffer construction is for high impact strength. All right, is for is for certain installation lah. Okay, for tight buffer. Alright, in a single mode fiber, you can see the core is very small. So since the core is very small, a lot of light cannot go inside the core, because the core is very small. It's just like a one pinhole. Alright, so what you need a very powerful light source. You need a very powerful light source that a lot of the light will be lost. So whenever the light that managed to go inside the hole, the light will be in the straight line. Whereas if you have a multimode fiber, the light, once you have in the light will be going like this. You can see here. Let me rub it off. The light in the multimode fiber, it will go like this. Alright. Okay. Whereas in the single mode, because the hole is very big, the single mode, the hole is smaller, so most of the light will go in the straight line. So because this one, the hole is smaller, so your light source, you have to be very powerful light source. Alright? So you have to pump in a lot of light here, and a lot of them will be lost because the hole is very small. This one you can have a less powerful light source. Alright? For this one, multi-mode, the light source will be not as powerful as the single mode light source. Because whenever you put in the light, the hole is very big, a lot of light can go through. So since this one travel in straight line, this one like this, so the distance for this one will be shorter. Because after some time you can see the signal and this signal, alright, this travel longer than this one, isn't it? Okay, so in this case, after some time, your signal will be, you have inter-symbol interference, alright? Okay, that means that you have one symbol like this and another symbol. Initially you have like this, okay, when you send, after some time it will be blur up, it will be like that, okay, because of the multi-mode. Okay, clear? Because the signal will get shifted. How do I resize it? Come on. Okay, now let's go on. Okay, so this single mode fiber. So dispersion means the spreading of the light pulse. Alright, so dispersion will lead to signal distortion and limit the bandwidth. Alright, so in single mode it does not have modal dispersion due to a single mode of transmission. Okay, so all the line goes inside straight line, single mode transmission. However, you have other type of dispersion such as chromatic polarized mode dispersion. Okay, the core is small, so the light is difficult to get in, so you need to use a powerful source, alright, such as high power laser. Alright, so these are the type of optical source. So you can use LED, normally you use in a CD player or laptop. This is the wavelength that is used by LED. It's low power, and then it has a large numerical aperture, poor coupling into the fiber. So because you use LED, all the light is spread out LED, so it's quite difficult to put the light inside the fiber. Okay, then you have a Fabry-Perot laser. So this is the wavelength. Okay, you can power up to few milliwatts, very polarized. You can go at gigabit speed. Alright, you have a more, it's easier to couple it into the fiber. Then you have a distribute feedback laser. This is the most expensive one. This is used in DWDM system. Normally it's a 1500 nanometer range. So it's used in CCTV and telco. Okay, so in the fiber optics there are three regions. The first region is this wavelength, second region is this wavelength, third region is in this wavelength. In between region 2 and region 3, the 1400 nanometer, that's where you have moistures. Alright, so this is the optical media where the signal coming in. Alright, electrical signal, you use the laser, alright, laser or LED. You confine the wavelength guide on the wavelength, then you transmit out the signal out. Alright, so on the receiving, So this is the fiber lah. This is the fiber. Okay. On the receiving, you have a pin diode that will change the optical signal to the electrical. So this is the signal and noise. Initially, this is what you send. After some time, it will become like this. Okay, scattering. So sometimes inside your fiber, inside the core, there is some impurity. You have some dust, crack. Alright. So what happens if the light goes straight and it hit the dust? So it will spread lah, the light. Just like you can see in Gerhana Matahari, or when the sun is blocked by the moon, something like that. So the light is spread, it will go on like this, scattering. Then you have bending. So suppose you have a fiber, you cannot put the fiber, you cannot bend it like a rubber band, cannot bend it like that, okay? Cannot bend, cannot over bend it, okay? So this is a micro bend, that means that there's some impurity of bending here. So when the light signal go here, and this one is macro bend. Macro bend is when what happens is that you take a fiber, like this, then what you're going to do is that you do like this, okay, 1 cm radius. So then you have a micro bend. Alright, so fiber end finish. So when you want to connect the fiber, you have to cut it, and then only you can connect, isn't it? So you have to somehow or other you have to cut it. So you have two fiber, you have to join it. Okay, so once you join the two fiber, they will have a air gap in between. Alright, if you are flat finish, there will be an air gap. Then you have another. Then apart from air gap, because you are flat finishing, this is a flat, then it's a mirror, no, the fiber is a mirror, it's a glass, so when the light come in, like this, it will bounce back, the signal will bounce back here. The same thing from, okay, if it's travel like this, it will bounce back, some of it will go through, some of it will bounce back. So what happens is that instead of having a flat finish, you have an angle finish like this. So when you send a signal like this, okay, the light, some of the light will go through lah. If it's bounce back, it will go on top, so it will not affect the sender there. You see that, top like that. Then you have physical contact, minimize back reflection. You have a round finish and ultra round finish. Ultra round service will be the best lah. Okay. If you are flash finish with no air gap, 4% of the energy will be reflected. So problem in multiple termination. If it's the dirt can enter into the air gap and can cause scattering and absorption. Then you have angle finish. The best is 8-degree angle. Alright, no reflection. Super physical contact lah. So you polish the end of the fiber, you polish it even more before you do the contact. Alright. So laser light can cause serious eyes problem. Okay. So you don't take the laser light and see, oh ada lampu this the last time you see the light lah. Okay, the light, you see the moment because even though it's few milliwatt but the few milliwatt is concentrated into one dot, into one dot. So you like that so you burn to your retina there, that part of the cell cannot see anything. Okay, so you want to see the light. Let's say you have the light source, you put it into a capture, then you see the light on the monitor. There's a monitor for you. Okay, don't okay. Then another thing is the fiber, the fragment is the glasses, it's very tiny one, very dangerous one, So sometimes it can, if you're injured or what, it can go into a blood slim one, you know, then it can die. So if you have a lot of this fiber fragment, especially in the lab where you use all the cutting, you cut, then you use the tape to stick the fiber and properly dispose it, especially the core. Alright, it's very tiny, more tiny than your head. Okay. So you must not scratch the fiber. You use alcohol solvent or lint-free gas. Basically, you need to swab, clean it up. Okay. So when you pour, to clean it, you basically use pressurized gas. Pressurized gas means that basically you use the gas to blow away all the thing. Okay. Then when you polish it, you should polish it with a 8 symbol. Like this, 8 symbol. You take the fiber and you polish it, because when you cut it with a machine, even though you see so straight, but then when you open up in the microscope and see, there's still, it will be still like this, you know. Alright, even though you cut it, it looks straight. So what happened? You have to polish it so that it becomes like this. Okay. Alright, so you have to polish it using the polishing film. Polish it so that it can even. One is roughly even already. Then another end. Then only you can join it together and then fuse it. Okay. Then next thing is splicing. Alright. So you have two types. One is fuse splicing. Fuse splicing, after you have cut the fiber, after you have cut, then you have polish it. Then you need two machines, because the fiber is so small, isn't it? So you need two. You need to put one fiber here, one fiber here. Then you use the machine to align it. Align it, you know. Align it and then measure it so that you pump in the light here. See how much light there is received overhead. So one is properly aligned. Then only you melt it and fuse the fiber. That is, melt it, fuse it together. After you fuse it already, then the fiber is joined in it. Then you still need to test the fiber. You send a signal here, receive. See how many you receive. So if below certain thing, then you have to drop it. Another thing is a mechanical splice. Mechanical splice. You join the fiber using the machine. Then there's a gap here, isn't it? So what happens in this gap? You're going to put in some fluid. Alright, some fluid. Because this is a glass, this is an air. The index difference is very big. So what we want is that we put in some fluid here. We want, when the light come in here, we want the light to think that the fluid is a glass. Alright, we want the light to think that it's still in the glass. Alright, and we will keep on throwing like this. Okay? So the fluid is something like a matching index. Okay? So this is the losses you are talking about, 0.5 dB. So okay, you need to align. After that, you need to test. After you connect to the fiber, you need to test. Send the signal here, receive here, see how much loss you have. Okay. Okay. So this is a power budget. So if you have a fiber single mode, if it's a short range 6 dB, that means you can tolerate 75% power loss. So your signal lost 75% of the power, you can still receive it. If it's a long reach, even if you lost 99% of the power, the link is still okay. So long reach, you're talking about probably 40 kilometer without repeater, 40 kilometer. Cable length, not distance. Okay, because normally the fiber you need to put in some budget. Okay, you will put some extra budget, because let's say you have the site here. you have one side here and you have another side here. Okay, you don't put the fiber like this. Okay, alright, normally you should put some spare here, and over here there's some spare here. Okay, because you don't know what will happen, and in most cases it's also not like that. It depends on maybe your fiber will go like that because the road is like that. You put under the road or something like that, or the rail will through. Okay. Alright, so this is the losses you're talking about. For 13 nanometer, you're talking about 0.4 dB per kilometer. This is the losses lah. For 15 nanometer, approximately 0.5 dB per kilometer losses lah. In the lab, you can have 0.18 lah. Okay, this is the losses in the fiber lah. So you need two fiber optics. So in case you want to have connection to the port normally you have two fiber optics. Okay, two pair of fiber. Any question on fiber optics? Any? No question? Sure? No? Okay, we stop here.